Okay, this is lesson 7.4, evaluating logarithms and graphing logarithmic functions for Algebra 2. And basically we're looking at, kind of our main focus is looking at what is the relationship between an exponential and a logarithmic function. I know this is going to be new for a lot of you in Algebra 2, so we'll try to go as slow as possible here. But basically logarithms and exponential functions. Logarithms really give us a way to solve exponential equations. Okay? If I want to try to figure out what power I need to raise something to get a certain value. So for example, if I had the question 3 to the x power is equal to 10. Okay? Now I know 3 squared is 9, and I know 3 cubed is 27. So I know this answer, x, is going to be somewhere between 2 and 3. But what is it exactly? Okay? I don't know what power to raise 3 to get 10. Okay? Even on my calculator, if I go, all right, well, 3 to the 2.1 power. All right, that's pretty close. That's 10.045. If I go 3 to the power of 2.05, okay, I get 9.50, not quite as close. I go 3 to the power of 2.09. Okay, 9.93. So I keep trying numbers. I do 3 to the power of 2. Instead of 1, I go 0.99. All right, now I'm getting closer to 10. Okay? But what is it exactly? What power do I need to raise 3 to get exactly 10? Logarithms are going to help us eventually solve that. Okay? So, well, first looking at an exponential function. An exponential function can be written as a logarithmic function. Okay? So if I have b to the x power is equal to a, how I write that as a logarithm is I do the word log, and then I write a subscript b, and that b is exactly what this b is here, so that becomes what we call the base of the logarithm. Okay? So it's the same as the base that we're raising to a power. That becomes the base of the logarithm. Okay, and then if b to the x is equal to a, then log base b of a is equal to x. So this logarithm calculates what this exponent should be. Okay? Now a couple of rules on that. A and b both have to be positive. They have to both be greater than 0. So it does not make any sense to have a negative base for a logarithm, nor can we take the log of a negative number. Okay? For example, on your calculator, the log button is in this first column. If I try to do the log of, let's say, -5 on my calculator is going to say, what? Okay? Non-real answer, that's an error. Okay, we've got a problem. All right, so whenever we're taking the log of something, it's got to be a positive number. It's got to be bigger than 0. Okay, for example, I can't even do the log of 0. That's not going to work. Okay, so let's take another exponential equation, and this is not really an equation. It's more, there's 3 to the 4th is equal to 81. We all know that's a fact. If I was going to write that in log form, it would be log base 3 of 81 is equal to 4. So 3 to the 4th power is equal to 81. So the value of this log is saying what number do I have to raise 3 to, what power to get 81, and that would be 4. So part of what you're going to have to do today is take a log or an exponential and change it to the other form back and forth. Okay, so here's another one. We have 10 to the 4th equals 10,000. So 10 is my base, so that would become the base of my logarithm. Now notice it's not written in there, it's left blank. Okay? Base 10 for a logarithm is what we call the common logarithm. When your base is 10, you technically do not have to write it in. If it's not written in, we assume the base is 10. So on your calculator, when you hit the log button, it's assumed that the base of that log is 10. Okay? All right, then we have the log base 10 then of 10,000 is equal to 4. So right now on my calculator, if I were to type in log, oops, move it over so you can see it there. So log of 10,000, I know that 10 raised to the 4th power is 10,000, so the log of 10,000 is going to equal 4. Now at some point we'll talk about how we do other bases of logs on our calculator, but for now we're just going to worry about base 10. Okay? All right, now another common logarithm is when you have a base of e. When you have a base of e, technically when you write that it would be log base e. But instead of writing log base e, we write natural log. Okay, or LM is the abbreviation for that. Okay, so log base e is what we call the natural logarithm And so for that, we use ln. So anytime your base is e, rather than writing log base e, we're going to write natural log. Okay, of 20.086 is equal to approximately 4. And you do have a natural log button on your calculator. That's automatically base e. Okay, so that's the ln button here. And then if I were to do the natural log of 20.086, which was on that problem, came out to be approximately 3. So actually, yeah, that's all we got. Whoops, I don't know why that says 4 on the worksheet right there. Sorry, must be just a typo from the first problem. So the natural log of 20.86 would be approximately 3, because that's our power that was written there. So that should be a 3. Okay? All right, so part of what we're going to do is we're going to rewrite stuff in exponential form. So give us a log equation. We're going to change it to exponential form. All right? So my base is 2, so that becomes the base of my exponential equation. 2 gets raised to the 5th power, and that's equal to 32. So that's how I change a log form to an exponential form. Okay? So looking at this one, we have log of 1 equals 0. Now remember, when the log base is not written, it's assumed to be 10. So I take 10 to the power of 0, and that's equal to 1. That's the same equation, only written in exponential form. So this one, my base is 1/5, so I take 1/5, raise it to the negative 2nd power, and set that equal to 25. Okay? Which we all know comes out right, because if I flip that over, it's 5 squared. And we all know 5 squared is 25. But this would be my exponential form of that log equation. Okay? So the next thing we need to do is we need to evaluate some logarithms. So if we know how to change it from a log form to exponential form, we should be able to evaluate it, as long as they're ones that work out perfectly. And these are all going to be ones that you should be able to work out without having to use a calculator. Okay? So what we know by looking at this is we have log base 3 of 81. What I'm trying to figure out is what does that equal? Okay? Some x value when I'm trying to evaluate it. So I'm going to rewrite it as 3 to that power is equal to 81. Okay? And now we have to do a little bit of thinking here, a little bit of calculation stuff. What I'm going to try to do is rewrite this number so that it's the same base as that side. I want to try to get the bases on the same side, bases on each side of the equation to be the same. So 81, we all know is, or hopefully know, is 3 to the 4th. Okay? If you're not sure, we can break 81 down. We know 81 is 9 times 9, and we know 9 is 3 times 3, and 9 is 3 times 3. So 81 breaks into 3 to the 4th. So since 3 to the x is equal to 3 to the 4th, then that must mean x is equal to 4, which must mean that that's the value of the logarithm. I have to raise 3 to the 4th power to get 81. Okay? And sometimes you're going to see them and recognize stuff right away. Other times you're going to have to do this equation. For example, if it was log base 3 of 9, you'll start going, well, I know 3 squared is 9, so I know the value of the log is 2. Okay? If it's a bigger number, sometimes you have to break its power down a little bit. Okay, this one. So again, I'm trying to figure out what does this equal. So I know 2 to whatever power I'm looking for is equal to 1/4. All right, now I'm going to try to make the right side have the same base as the left side. So first of all, we all know that 1/4 is the same thing as 4 to the negative 1 power. Okay? Or if you want to think of it as 1 over 2 squared, and we can rewrite this as 1 over 2 squared like that. That might be another way to look at it. Okay, now we know 4 is 2 squared. So I have 2 squared raised to the power of negative 1. We all know that we can multiply the powers in that case. So we have 2 to the x is equal to 2 to the negative 2. And therefore x must be negative 2. And that's the value of the logarithm. Well, what I also could have done up here was once I got 1 over 2 squared, then I know I can rewrite that as 2 to the negative 2nd. And then I could have gone straight to knowing the value of the log would have been x equals negative 2. So I have to raise 2 to the power of negative 2 to get 1/4. That's the whole thing we're trying to figure out. Okay, the next one we have 1/4 to the x power. I'm trying to figure out what makes that equal 256. Okay? Now for me, on the left side of this thing, I'm going to rewrite this as 4 to the negative x. I don't like dealing with fractions, so if I flip it, I can just make it a negative power. Okay, 256, if you break it down, breaks into 4 to the 4th power. So if I have 4 to the negative x is equal to 4 to the 4th, then that must mean that negative x is equal to 4, which means x is equal to negative 4. So the value of that logarithm must be negative 4. Okay, this one, I have 10. I want to figure out what am I going to raise 10 to get 0.001. Now 0.001, I don't like to try to figure out what makes a decimal in this case. Now remember, this is the tenths, the hundredths, and the thousandths place. So if I have 1,000th, that's the same thing as 1 over 1,000. Okay? Now, anytime I have 1 over 1,000, okay? Now 1,000 can always be written as 10 to a power. 10 to a power, 10 to, or 1,000, just count the number of zeros, is the same thing as 10 cubed. Now, if 10 to the x is equal to 1 over 10 to the cubed, remember 1 over 10 cubed is the same thing as 10 to the negative third. So therefore, x must be equal to negative 3, and that's the value of my logarithm. Now, in the case of 0.001, the other thing I can do is I can say, well, I have to move the decimal point 3 places to the left, so I know I have to raise 10 to the negative third power to get there. Therefore, the value that's going to be negative 3. Whatever works best for you. Okay. All right, this one, I want to figure out 9 to what power is going to equal 3. Now, the 3 over here I can't change. I can't get that reduced anymore. Okay, so it's just 3 to the first. So what I'm going to do on this one is I'm going to try to make the 9 look like a 3. Well, we all know 9 is 3 squared, so I can rewrite 9 to the x as 3 to the 2x. And on the other side, we have 3 to the first. Now that I have the bases the same, that must mean my powers are equal. So 2x is equal to 1, and therefore x has to be 1/2. And there's the value of my logarithm. So I have to raise 9 to the 1/2 power to get 3. Well, 1/2 power is a square root, and the square root of 9 is 3. So the value of my logarithm has to be 1/2. So you want to set all those up as exponentials. Okay? And then you want to get your bases on each side to be the same. Once your bases on each side are the same, then you set your powers equal to each other and solve for your power. Okay, then they have some they're going to ask us to do on the calculator. So for these, I'm literally going to type it into the calculator. So we have log of 0.85. And remember, there's no base written, so it's assumed to be base 10. So on my calculator, I'm just going to simply do the log of 0.85. Okay. And let's go out to about 3 decimal places on those. So that's approximately negative 0.071. For the value of that. It means I'd have to raise 10 to that power to get 0.85. If I do 10 to the power of my last answer on my calculator, it's going to come out to be 0.85. That's what we just calculated, that number. Okay, next one says natural log of 22. So I'm just going to do the natural log of 22. Comes out to be approximately 3.091. And remember, natural log is base e. So what I've just figured out is if I take e to the last power, or the power of my last answer, that's going to come out to be 22. So my calculator is calculating what power do I need to raise e to get 22. Okay, some properties, and specifically these are called inverse properties. Okay? If you have a base, and let's say you're raising that to a power of a logarithm, if the base and the log, or the base of the log, are equal to each other, and you're raising this base to this power, and the answer is just going to be whatever is right there. Okay? I can simplify that down. So for example, on this one where it says simplify the expression, okay? I'm going to zoom in just a little bit so we can see that a little better. And of course, you have your note sheet. I have 8 to the power of log base 8 of 5. Well, I look here and I see the base is 8 here and the base is 8 there. I can simplify that to just 5. Simple as that. Also works if I'm taking the log of something that's raised to a power with the same base. Okay? So if I have log base b of b to the x, well then the answer is just going to be whatever x is. Because remember, it's the question when I'm doing a log is what power do I have to raise 5 to to get 5 to the negative 2x power? Well, that would just be negative 2x. So it just simplifies to that, as long as those are the same. All right, we have 2e to the natural log of 9 power. Now remember, this is a base is on this is e, and we're raising to a natural log. Now remember, natural log is log base e. So here I have the base, and the base on my logarithm's the same, because a natural log has a base of e. So that's going to simplify to just be 9. And then I have 2 times 9, which is 18. So the e to the natural log of 9 simplifies to just be 9. And then 2 times 9 is 18. All right, so this one we have log base 3 of 27 to the x power. Now, it looks like I can't really use my properties here because 27 and 3 are not the same, so I can't simplify it yet. But hopefully, you remember that we can change 27 to 3 cubed, which means I can rewrite 27 to the x as 3 to the 3x. And now I can use my property. This base and that base are the same, so therefore the value of that is just going to be 3x. All right, those are my inverse properties of logarithms, just like that. So again, it's when that base and that base are the same, or when I'm raising something to a power, like this one, where that base and that base are the same. I can simplify it. Okay, then we're going to have some problems where they're going to ask you to find the inverse of an exponential or a logarithm equation. Now, if you remember back to last chapter, one of the things we had to do was find the inverse of functions. And what we first learned was we have to switch the x and the y. So I have to put the x here and the y there. Okay? So that's the first rule of solving for inverse functions. Whoops, sorry, my lights went out in the room. Hang on just a second. Okay. All right, so we have x equals 8 to the y power. Now what I'm going to do is once I have an exponential equation like this, and I'm trying to solve it for y, I'm going to change to log form. Okay, so if I have x equals 8 to the y, I can change that to log form by taking log base 8 of x and setting that equal to y. Okay? So this is what we learned earlier in the lesson. If we have x equals 8 to the y, that's the same thing as log base 8 of x is equal to y. So when you get an exponential equation, to get its inverse, you want to change it to log form. Okay? All right, let's try this one. So first of all, we're going to switch the x and the y. So we have x equals 2 times 5 to the y minus 2 power plus 1. All right, now before you go to change anything to a log equation, you need to get the exponential by itself. So I'm going to need to get this right here all by itself before I change to log form. So I'm going to subtract the 1, and I'm going to divide by 2. So x minus 1 over 2 is equal to 5 to the power of y minus 2. Once I get to there, that's when I'm going to change it to log form. Okay? So remember back to our log form, this becomes the base of my log. So I'm going to change this to log base 5. I'm going to take the log of this expression, so of x minus 1 over 2, and that's going to be equal to the exponent y minus 2. Sorry, I'm going to move that over so you can see it. Okay? So again, I've changed it to this is the base of my log of this expression is equal to the exponent. Okay? Now the last thing I have to do is I need to get y by itself, so I'm going to bring the 2 over. So I have log base 5 of x minus 1 all over 2 plus 2, can't combine those together, equals y. And there's my inverse function. Okay? Now those were exponential functions and their inverses were logarithmic functions. Well, now we're going to take logarithmic functions and their inverses are going to become exponential functions. All right, so in this case, I'm going to switch log base 4 of y minus 2. We're going to switch x and y. Okay, now before you change the exponential, we need to get the logarithm by itself. So I'm going to divide by 3. And now I'm going to change this to log form. Okay, so log form says I take the base of the logarithm 4, I raise it to this power, so 4 to the power of x over 3, and that's going to be equal to y minus 2. And then I got to get y by itself, so I'm going to add the 2 to the other side. So I have y is equal to 4 to the x over 3 power plus 2. Okay, started out with a log equation, inverse is an exponential equation. All right, so one more of those. Now I switch x and y. Okay, now I have to solve for y. So the first thing I'm going to do is get this log by itself, so I'm going to subtract 5 from the other side. Once the logarithm's by itself, then I'm going to use the exponential form. Now remember, since we're dealing with natural log, the base is e. So e gets raised to this power, so it's e to the power of x minus 5. It's going to equal y minus 2. And then I'm going to add 2 over. So y is going to be equal to e to the x minus 5 power plus 2, like that. And there's my inverse equation. Switch x and y, get the log by itself, change it to exponential. If it's an exponential form, get the exponential term by itself and change it to log form to solve for the inverse. Okay, graphing logarithmic functions. Now first of all, we're going to take a look at the parent graph for logarithmic functions. Okay? All right, so first of all, remember how an exponential function had a horizontal asymptote at the x-axis. Well, the logarithmic function is the inverse of the exponential function. So a logarithmic function is going to have a vertical asymptote, and the vertical asymptote is going to be the y-axis, which the equation for that is x equals 0. Okay? Remember I told you before we can't take the log of 0. There's nothing that if I raised it to a power is going to give me 0. So I can't plug in 0 into this equation. Okay? So let's go to 1. Okay? So the question would be log base b of 1. Well, what power do I have to raise b to get 1? Okay, remember b's got to be some other number. Can't just be like, 1. I'm going to raise 1 to the 1 power. Okay, b could be anything. So let's say b is, 5. What power do I have to raise 5 to get 1? Okay? Well, remember, anything raised to the 0 power, except for 0, is equal to 1. So anytime you take the log of 1, it doesn't matter what the base is, the answer is going to be 0. So we have a graph, or a point, at 0, 1. Or excuse me, at 1, 0. When I plug in add 1 for x, I get 0. Sorry about that. So the point at 1, 0. Remember, on exponential functions, we had a point at 0, 1. So on log functions, we're going to use 1, 0. Now, if we plugged in b, if we did log base b of b, well, log base b of b would be, what power do I have to raise b to get b? Well, that would just be 1. That's another point we're going to use, is whatever the base of our logarithm is, and 1. And here's what the function looks like. It goes up slowly through there and keeps increasing. And then the graph gets closer and closer to the y-axis, but never hitting the y-axis because remember we can't take the log of 0. So the domain is x is greater than 0. The range goes all the way down to negative infinity, goes all the way up to positive infinity, so the range is all real numbers. Or remember we can write y is an element of the set of real numbers like that. Okay? So there's our basic logarithmic function graph. We have 1, 0, and whatever our base is, 1, we're going to use those 2 points to move it. Okay? All right, so for our parent function for this particular graph, we have y equals log base 4 of x minus 2 plus 4. My parent function, I'm just going to look at log base 4 of x. Now I know it's going to have a point at 1, 0, and another point is going to be whatever the base of the logarithm is, 1. Okay, we know that it's not stretched by anything because it's not multiplied by anything. There's no something out here times the log, so there's no stretch or reflection on this one. The minus 2, we hopefully know is going to move it right 2, just like it has for other graphs. The plus 4 on the outside is going to move it up 4. So 1, 0 is now going to be at 3, 4, and 4, 1 is now going to be at 6, 5. So on my graph, I'm going to go up to 3 or over to 3 and up to 4. I'm going to go right 6 and up 5. 1, 2, 3, 4, 5. My vertical asymptote moved 2 to the right, so it's now here. And I'm going to draw my graph going through those 2 points and then down towards the vertical asymptote, just like that. Okay, so one more of those. This one we have log base 6, so I'm going to use that as my parent function of just log base 6 of x. I'm going to have my point at 1, 0, and another point at 6, 1. Okay, there is a stretch on this one and a flip because of the negative 3 that's being multiplied out there. So I'm going to take the y coordinates and I'm going to multiply them by negative 3. So 1, 0 is going to still be 1, 0. 6, 1 is now going to be 6, negative 3. The plus 2 on the inside is going to shift our graph left 2. The minus 1 is going to shift it down 1. So 1, 0 is now at negative 1, negative 1. And 6, 3 moves to 4, negative 4. The vertical asymptote moved left 2. So I'm going to move that dashed line to there. Negative 1 is here. 4, negative 4 down here. And now my graph goes through those 2 points, continues like that, and goes up towards that asymptote like that. Okay, one thing I failed to mention on the last problem was the domain and range. Let's talk about that. Okay, so the domain on this one, we can see we're at 2, and we're to the right of that. So domain is going to be that x has to be greater than 2. Range is going to be all real numbers. Notice that's kind of switched from exponential functions. With exponential functions, the domain was all real numbers, and we had a restriction on the range. Now that's switched with logarithmic functions. On this problem over here, we move to the left 2. Our graph goes to the right of that, so our domain is x is greater than negative 2. And our range is all real numbers. Graph goes to positive infinity all the way down to negative infinity. Okay, that's section 7.4, evaluating logarithmic functions. We also did some inverses of those, of exponential and logarithmic functions, and then some graphing of logarithmic functions. Okay? All right, and if you have any other questions on that, you can ask me in class tomorrow as we're working on these problems in class.